and welcome back to a new video in my C++ tutorial series here on the Ludwig Fusel channel. In last video we have talked about creating your classes and adding constructors and destructors. So basically what we have done is we have added these three functions that were automatically called when an object was created and the function that was called when an object got destroyed. So we write a class, we instantiated an object, for example down here the PEC, then automatically setup was called, and when it got out of scope, release was called, and the object's data was freed and returned to the operating system. So in this video today, we want to now talk about a very important concept in C++. We want to talk about the concept of references and Const correctness. Now, this is all sounding quite intimidating, complicated, and out of context. And again, what I try to do is I try to construct us a problem, and as soon as we have constructed this problem, we're going to try to solve it, and we're going to end up magically at our reference and at our Const correctness. So let's get started and do something. Alright, so what do we want to do today? Today I want to change responsibility. I want to change the responsibility of printing the function precacher out of the main function to a dedicated function that should just print the precacher. So what I want to write is I want to write a function void do work, or let's just call it print PC because it's printing a precacher, and what it should do is should print on the PC, and maybe before it does say SCDC out, here comes the PC, and then the PC is going to be written, so something like that. That's what we want to do in that little function here, and then instead of calling this down here, we want to call that function. Alright, of course, when we want to do this function, we need a parameter. Now, the most obvious thing you would do is you would add the type in here, which is the function precacher, and we would add a name, so function precacher PC. Now this function seems syntactically correct, and we would be ready to call it. So instead of calling print down here, I would call print PC, and we should now get a proper output from our PC. So let's press F5 and see what this function does. Alright, so enter the starting value 5, enter the iterations 5, and what is it doing? What's going on? It hasn't tapped us in, but actually you can see that the execution of our application halted, and we're gonna get an error here. Breakpoint instruction executed. A breakpoint instruction statement or a similar call was executed in simple CPP app. Alright, so you can see we kind of like had an issue. If I would click continue on, you would get the message box with debug assertion failed, expression. What do we get here? CRTSLS valid heap pointer block. Whatever. So basically the idea is we are getting a error here, a runtime error, because something has gone wrong. And if I would go in and debug, yeah, we would now need to solve the issue. So our application failed here. We had an issue in that file that is containing by the C++ standard library. We really don't care what's going on, but in general, we had an error here. So let's actually stop the execution and try to figure out what has gone wrong. Alright, so what has happened? Where does the error occur? I'm going to quickly start this again so that we are on a fresh instance and I can directly see where it was. Alright, so now we are back again here and we are back again at the breakpoint instruction executed. So we have an issue that occurred in that function, and that function that had the issue is called delete of a void pointer. So actually, as you can see, when we are deleting an object in C++, the delete operator, we always use delete and then a pointer. The delete is actually implemented by this function, and you can actually see that this is calling the free function of Microsoft, and the free function of Microsoft occurred an error. So you can actually see down here somewhere in ntdll.dll we had the error. We can't see it because we don't have source code of that available. And if we would go up as far as we go, we can actually come up to the way where we had that issue. Microsoft is always trying to show us the first thing that we know, and this is the delete operator. If we go one level up again, it's all down here by the way in the call stack. If we go one level up again, you can see that we're now in the delete array operator. So the delete array operator actually was the one that was invoked by our application, and this one called the operator delete, so the normal delete with the same block, so it's basically just passing on the data. This is also why on Windows it might be okay to just call delete instead of delete array, but if you're not on Windows or special compiler on Windows or special version of the Microsoft compiler, it can be an error, so always use the delete array, but that was all about last video and the video before that. So you can see the error occurred somewhere in delete array, and if I go even further up, you can see, alright, actually the error occurred here in the delete values call of our application. So delete values was the one that showed us an error. And if we go even further, you can see that release was called by the destructor of the function precacher. And if we go one time higher, you can actually see that this is the code that was executed, so the cleanup code when the main function returned, which was calling the destructor of PC. And this is kind of like the history of our error. Now we need to try to solve it. So we can see that the issue was by deleting our object here. So basically what happened is the error was being executed here. So let's actually try to instrument this code and print some metadata. All right. So what I want to print is I want to call destructing off, and then I want to just echo out the sys pointer. If I echo out the sys pointer, we're going to get the pointer address so that you can see what's going on. So I just want to echo out the sys pointer so that you can see what's going on here. Since we're on C++, this all works. Okay, so I want to instrument this code. So now let's also instrument the release code and also the allocate code. So the release code and the allocate, this one was allocating. So let's stdc out it as well. So allocate, of course, allocating values so that we have a pointer as well, so that we can see what was allocated and in release before we delete it. We want to say stdc out, deleting, because we're now deleting, it's not done yet, deleting also values here, right? So now I set the handle here, so std handle. Now that we have some instrumentalization code in here, let's try and see what it is doing. Alright, so let's rerun the application by pressing local Windows debugger and see until when we are getting our error. So let's press 5 and 5, and now we have the error here. Let's open up the console and see what happened. Okay, so let's see what's going on. So the first thing that happened is that we allocated that object, or that array. This was actually allocating our values pointer. So our values pointer is ending with 660. The next thing what we have done is we have destroyed an object, the object dff_e0 ffce0, and this destruction of that object actually resulted in deleting the following code, the following object here, which is 660, which is what has allocated here. But you can see after we deleted that, we again destructed an object. Now you can see that this object has a different address. Here, that one, it was ffce0. Now we are deleting ffbe8. But while we are destructing ffbe8, you can see that we again try to delete 660. So you can kind of like see we are trying to delete the memory block that we have allocated once. We are trying to delete this twice. Okay, so why are we deleting this twice? Well, we could try to find this out. How can we try to find this out? Can we try to find this out? Maybe we could by also instrumenting what our application is doing. All right, so let's try adding some instrumentalization to our application. Maybe we want to also echo something out here in the constructor and say something like constructing. I don't know why I'm saying something different than I'm writing. Normally it's always harder to write something differently than you're writing, but yeah. So let's also instrument this with constructing. Maybe we might even want to instrument our default constructor. However, this is not going to be useful, so I'm going to omit this by default because default constructor is actually never called. But let's maybe instrumentalize our code a bit. So let's instrumentalize this here. Let's say creating PC. That is something that I want to do here. So we are creating PC. And now down here, I want to say computing on, and we're going to take the address of PC so that we know what we're doing here. So now this is on the stack. Now I need the address operator. Then we are computing on this. That's good. And then let's see out here again. Calling print PC4. And then we are calling this for our PC again. So let's say PC here, and let's do an handle. And now let's go into our print here, and we're gonna call. We told that here comes the PC. I actually wanna remove this. I wanna output printing with. I wanna say printing with, and I wanna print with the address of PC again. And then we'll PC print. And now that we have that many instrumentalization code, let's press F5 and see what we get. So 5 and 5 still going to give us the error. But now let's take a look on this. What's actually happened? All right, so let's start by seeing what's going on. So the first thing that we are getting is the creating PC. All right, creating PC is done. Constructing this object. So 8 now, they have, of course, new addresses because something called random address offsetting, or how this is called. Basically, in general, every time you start your application, you're going to get different addresses. This is just how things work, to be a bit more random and to solve errors that might be there. However, you can see like that we constructed the object which ended with F898. You can see that we have done the computing on it and it was fine. While doing the computation, we have allocated the memory block 25D0. Then we called print PC for that F898, so still the same address and above here. However, as soon as we were inside the print PC function, you can actually see that now the address has changed. So we called the function with F898, but now you can see that the actual print function is operating on the object F990. So you can actually see that we get a new object when we go into the function that printed the data. So inside of the function print PC, we have a different address of that object than with which we actually called the function. Now you can see it's doing its printing, it's all working. However, as you can see down here, it's now trying to destruct this, and actually it is destructing the object that has been created, or the object that was actually used for printing. You can see printing, it has created this new object called F990 instead of the F898. So this is a different one. This is the original one. We kind of like have a new one, a new copy here. And actually you can see when we are going out of that function, we are also destructing this object. So the object is being destructed. The F990 one is destructed. While the F990 one gets destructed, you can actually see that we deleted 27D0, which is the one that has been allocated previously. And remember, the allocation was done by the object of F898. So F898 allocated 25D0, but F990 has deleted 25D0. And you can see this is now where we are returning from the function, and now we are back in main. Now you can see we have our original object. Our original object gets destructed, so the original F898 gets destructed, and you can see the old one, the original one, which allocated that originally, also tries to delete this. So you can see still the same. We are trying to delete this block of memory twice. And you can see if we delete something twice, it's not possible, because if it has already been deleted, it doesn't make sense to delete it once again. Now, this is the main issue here. We are trying to delete it twice. One times from the object F990, and one times from the object F898. So two objects, both getting deleted, and both of them trying to delete the same memory block, and this is going to give us an error. Alright, so why do we have that error now? Now let's consider our knowledge that we know from C. As I've told you in C, if we are just passing the objects around, we're going to get a copy. If we have an int and we pass it to a function, we get a copy of that int. If we are modifying that int, the original one is still staying the same. And this is the same thing that happens here. The print PC is having a plain function precacher PC. So actually what happens, as soon as you call this function, the C++ language, or the compiler, or whatever you want to call it, the computer, it creates a copy of the precacher. Now, how can it create a copy of the precacher? Well, this is a concept called the big three, or related with the concept of the big three. And what's happening there really is that we are getting a plain copy of that object. So what's it really doing? It is copying all that member variables that are in here. The value, the x, the count, and the function. They are plain copied from left to right. And if you're doing this, you're getting an exact copy of that object, which is fine for printing, because, well, we have the pointer to the same array of data, we have the same function, we have the same x, we have the same count. It's still the same data on the object. They are completely identical each other, but we are getting a copy of that. And if we're creating a copy, this copy also needs to destroy it. Now, when the copy is destroyed, it is calling the destructor. And if we are getting inside of the destructor, we are calling release, and the pointer gets released. However, it is only released here at the copy of the object. So the copy of the object, this one gets the proper call to release. The release call is also setting the values to null pointer, and everything is good. But only with that copy. As soon as we are returning to the main function, the copy is discarded, but we are still left with the original PC, and the original PC gets destroyed again. It still has the old state in there, so the pointer has not been set to null pointer, and this is gonna then result in the error that the release function is called again. The pointer is still valid for the original object because just a copy has been set to null pointer, and it tries to delete the same memory block again. And this is going to result in the error that you have seen because we tried to do it twice. And actually you can see if you take a look at the output here in the debug output, heap simple cf.exe invalid address specified to RTL validate heap. So RTL validate heap, it got two addresses here for whatever they did, but basically they were invalid. This function validate heap tries to validate the call, and it basically said, all right, okay, the this was not valid, and then it's gonna introduce this breakpoint instruction, debug break, which basically brought us into the code, and we kind of like were there and said, okay, debug instruction was executed, there was an error, and this is basically what happened. So the issue is that we are getting a copy of that object. However, we don't want to have a copy. Okay, so let's fix it. We already can fix it. Very simple. We can take a pointer to that, and then we can do this like that, and then we can execute a normal print here. If I do a pointer of that and try this out again, okay, of course I need to enter a pointer down here as well. So let's give this one a pointer as well. And if we're now trying to do this, enter the value, 5 and 5, you can see our function works like a charm. So you can see we are constructing the object fc18, we are computing on fc18, we are allocating 2060, we are calling printf for fc18, we are printing with fc18, we are destructing at some point fc18, and we are deleting 2060. So you can see if we do this as a pointer, everything works well and everything is good. And we have solved the issue. Now, this is not a new news for you, just something you need to be aware of. You already know how pointer works from C, and you know the theory behind it. But the news here for you is that you need to use a pointer there as well. However, I personally don't want to use a pointer here. Why do I not want to use a pointer here? Well, because if we have a pointer, somebody could be as bad and put a null pointer in here, right? So somebody could call this print PC with null pointer. What happens if we do this with null pointer? Let's try this out. 5, 5. Boom. This was null pointer. Now this is some error that is looking quite different, because now we are actually inside of the print function of the object, and this then said that this was null pointer. Basically what happened is print PC tried to call on PC print, and PC is null, and this is why inside of the function here you can see as soon as we are tried to access, is it the next one? Yeah, it already validated that when we are going into print. And then it basically detected, all right, no, I'm null pointer, okay, this is going to be an issue. And boom, you're done. Everything is bad. Everything is broken. If you would click continue, it doesn't work. I don't know why you have the option to continue, but this is unrecoverable. Some of these issues are recoverable, this one is not. So you can see, something was wrong. Also here, exception shown, 3-axis violation, this was null pointer. We're getting many issues here. So as you can see, like, it doesn't work. Okay, so how can we fix that? Well, we could fix it by checking that. Okay, so if PC do that. Okay, so now it looks good. If this is PC, we can do it. And if we try this out like that, 5, 5 works again. Alright, so this is a very nice thing. Okay, however, what we are doing here is we are having an if in here which wastes CPU cycles. We are we need to add this ampersand here, which is wasting not CPU cycles, but which is hard to type. You always need to remember that you add an ampersand. And if you are seeing that there can be a null pointer, people try to put in null pointers because, yeah, it's a pointer, let's try null pointer, right? And many of these things can happen. Like, it is not very clean. Why do we need to do this? Well, wouldn't it be nice to just put the object in like that and have it automatically validated? And yes, actually we have the option. There is a way to do non-pointer passing but not creating a copy of the object. So if we have done this like that, we have created an object of the copy. If we have done it like that, we have used an address, but we haven't created a copy. However, what I want to use it as plain as that, but I don't want to create a copy. And this is where references come in. So in C++, we have pointers and references. Pointers are plain pointers then in C++, so you can get the address of an object in here, you can check if it is null pointer, you can pass a null pointer, and everything is good. However, in C++, the references work a bit different. References, in general, disclaimer, are just pointers in the end. But what the C++ language is asserting is that a reference is never null. So a reference is kind of like a non-nullable pointer. How can you create a reference? Well, a pointer was there, the star was there for a pointer, and for a reference we use the ampersand. You already saw this at some peaks which I have done, and as you can see here now, I'm adding the ampersand, and the ampersand means, alright, this is a reference. It's in general similar to a pointer, but or what's really happening in reality. It's a pointer, it's just an address, but in this case it's kind of like in reference, it works like an object, so the pointer operator doesn't work with that. You can of course create pointers from that, but you can see like from the syntax, the PC is now working as simple as an object, so it looks like an object. It's as you can see, syntax, if I have no reference there, or if I have a reference there, the syntax is going to be the same. The same down here, PC works like that. If I remove the ampersand, works as well. So it really, from the syntax away here, is looking like we are passing in a plain object, not a pointer. So you don't need to have addresses there, and you don't need to deal with that. So really what it is a nice shortcut to put in some data without having to deal with all that pointer madness, with checking for null pointer and stuff like that. So kind of like a minimal, lightweight pointer. And of course, you can do this as well in your function. So let's first maybe remove all that instrumentalization, because we no longer need them. Maybe we wanna, yeah, we could keep them. Okay, so maybe, okay, I'm gonna quickly, just to show you that it works, quickly gonna put them instrumentalizations back and start this with the reference so that you can see that it works with a reference as well. So the reference is acting the same as a pointer. So we are constructing the object f818, we are computing on f818, we are allocating 39 is 0, we are calling print PC with f818. Print PC actually got the f818 there as well, so it kind of like was like a pointer passed to that function, not copied. And then we are destructing f818, which was deleting 39E0, which was actually the memory block that we have allocated. So you can see it works the same. Then if we would have used pointer, but from the syntax, it looks very simple. And also like you're passing PC, not a pointer. In general, like the pointers are more like used as an option argument in C++. If you have a pointer in C++, it's more like, hey, this is optional. You can also put a null pointer here, even though like everybody does what he likes, and many people coming from C don't use references, and I personally, when I started with C++, didn't like the references as well. However, they are required. If you want to do C++ properly, you need the references. It's important, more important than pointer actually, for C++ in general, even though pointers are still like more important from the general knowledge. But for C++, especially writing classes, the understanding of an ampersand is nearly as or even like, let's say it's the same important as a pointer. Both you need to know both of them. So yeah, that's the idea behind the reference. Now, I'm gonna continue after removing the instrumentalization. I do want to quickly get rid of them quickly because we don't need them, and then we want to talk a bit more about what's going on there. This one is still missing. Okay, so now we have removed all the instrumentalization. Let's run this again to see that we are getting just our plain output. Yeah, everything works. Okay, good. So now let's do a bit of play around with these references. So we had pointers, we had const pointers. Do we also have the option to use const references? So in this case, print should not modify this, right? The function precursor should not be modified. It should just print. So we can use like a const reference. Can we do that? Okay, yeah, it seems like we can. You can see const reference, it's all looking good here, but you can see if we're using a const reference, we got an error here. What is the error? Let's hover over that. The object has type qualifiers that are not compatible with the member function print. Object type is const function precursor. All right, so what's happening here is now that actually on C++ we have a difference between const and non-const. On C in general, it was a bit easier. On C, it was more like, yeah, you can't modify it, but you can use it. On C++, it's more different because you have functions, and it's not as simple as that. It's not as simple that the function automatically knows if you are calling it const or not. In general, what we have in C++ is something called, or a concept called Const Correctness, and this means that you need to write your classes with proper const specifiers. So you basically need to do, if you're writing a function inside a class, you need to validate if this function can be constant, right? So like the constructors and destructors, they don't make sense because they're creating the object. This is const. So const means don't change the object in general. What are we doing on setup? Well, on setup, we are assigning values, so const won't be good. I could try to add const here, but you can see if I add const here, it's actually written after that function here. So you can have the function body here. And after that, you write const, which basically means that this function is in a const context, but you can see that we can't access it. Expression must be a modifiable L value, whatever that is, but basically we are trying to assign x to this x, which doesn't work because we modified this function to be const, so this function definitely makes no sense to be const, so I'm going to remove that const. What are we doing at compute? Let's try this out. Well, we can't assign values or call release because release is not marked as const, so we can't call it, and we can't assign values because it is marked as const. Alright, so let's remove const. It doesn't make sense here. Release, would it make sense here? Well, it deletes values, so it's not really something that you should do. And actually delete would work, but assigning values to null pointer would not work, because this is like, the delete operator is reading values, and this is writing it. So delete works, but writing doesn't work. But still, release, it doesn't make sense. However, we have our print function, and our print function, well, it's just reading values. So this would actually make sense to mark this function as constant. If you take a look at this, I write const, and we don't get any errors. You can see everything looks good, because we can actually mark this one as const here, because it's not modifying anything. And just by marking that one as const, you can see that magically this one is going to work, because now this function is marked as const. Actually, if you're typing PC and at a point here, you can actually see which has been marked as const. You can actually see that print is marked as const, and all other functions are actually hidden, because, well, they are not const. And if you have a const reference or a const pointer, it doesn't matter. If we would have a const pointer, still the same thing, right? If I would say PC, you can see print, it's still giving that. The concept is the same, no matter if it is a pointer or a reference, or actually even an object. You could, of course, also create like a const function precacher. If you're doing a const function precacher, of course, it doesn't make sense, because it never computes something, and you can't call this. You can see this wouldn't work, but if I would call print would work, because it's const, right? But this doesn't make sense here. However, as function calls, having a const reference is something that is really, really common to use, and is also something that we need in the next video. This is why we are talking about all of this. It is good, because really what it is doing, it is not modifying that PC, it's just printing the data from it, and printing the data is not modifying the object, and this is what you call const correctness. So const correctness means that every function that gets something as a parameter, doesn't matter if it is a pointer or a reference, if it is a pointer or a reference and you don't change the object itself, you're just reading from it, you should mark it as const reference or const pointer. The same goes for functions. If you write a function that is not modifying the internal data of the object, so it's not really changing something, you should also mark it as const, right? And if you mark this as const, it is allowing you to call it in a const pointer or in a const reference. It's allowing you to use that here, because you kind of like mark this as const. This is not going to change the internal state of the object, so everything is good. Actually, there's one exception to that. Actually, you can do something. So if I would add some variable like this one, modify me. So if I would add this modify me to 0, and this modify me is kind of like trying to count how many times you access that, you can see that if I would increment this here, it is not allowing that. Actually, what you can do here is you can add the word mutable. If you would add the word mutable, then you basically mean that this one and single variable is allowed to be mutated in a const function. So mutable is an access modifier that you can write before that type here to make that one and single variable addable in a const function. This is not really something that you need quite common, but for example, if you're writing a class that can be accessed from different threads and you want to have const correctness there as well, but it still needs to be locked, so only that one thread can access that, you can have your log object and mark this as mutable, so the log can be used even from a const function to allow just one thread to access it and to guard this. But that's a bit more advanced topic here. So in general, just mutable, so just as a side note, is basically, yeah, like disabling the const checkings for your own function. But in general, const correctness, if a function doesn't modify content of the class, mark it as const here after the function name and the parameters. And if a variable or a parameter to a function shall not be changed, mark it as const, a reference or a const pointer, or even as a const object, so that it doesn't get changed there. And you only have access to functions that don't change the integrity of that object. And that's the whole idea of const correctness there, and references. So references, just pointers that can't be null. Right, I think did I try to show this to you? Print PC with null pointer now, of course, doesn't work, because it needs an object. That you could write, that you can give it a function precacher. Yeah, sure, you can create an object and it can be 0. So you can create a function precacher with like x count and f again and put it onto there, but it wouldn't do anything because it never computed. Right, if I would do this like that, it only gives us one iteration because it doesn't compute. If I would have an automatic computation there, it would of course work, right? If I would go up again, I would do something like call compute here, and the constructor automatically as well. If I would do this, then we should get twice the output, because this would automatically call compute, and then we have a valid thing there. However, that's not what we want to do here yet. So the idea here is just that we can now also call print PC. I mean, the reason for calling it, it's really not there. It's more like to show you off and show you how the references work, because we need the reference next time. And what we're going to do next time is we're going to solve the issue that a copy of the object is going to ruin us. Again, doing a copy of it, even if it's const, is going to ruin us. Debug break. Because still, if the copy is const, it's still gonna delete us. And that's what we want to solve next video when we talk about the big three. So thank you for watching. I'll see you in the next video. Make sure to like and subscribe, and have a nice day. Bye.